Rohit Kumar Singh, and I'm the teaching assistant for this course, Statistical Mechanics, and this is the 6th live session. And this course is being taught on NPTEL by Professor Dipanjan Chakravarti. So I hope you guys are following the lectures there. And so today I'll discuss some concepts of the canonical ensemble, and we'll try out some problems based on that. Okay. So last week we looked at what ensemble means and what is microcanonical ensemble, and then we did some problems based on that. So I hope you guys were able to understand that. So okay, so yeah, but last week in the microcanonical ensemble we saw that. So I'm denoting microcanonical ensemble by mu. Okay, so there we saw that everything was fixed, right? So obviously the number was fixed, volume was fixed, and energy was also kind of fixed, because we were taking the energy from some range, right? From E minus half and E plus delta by 2. So energy was also kind of fixed in a range. But this is not a very ideal situation, right? In general, if you have, it's very difficult to keep the energy constant of any system, and also you cannot control the energy. You cannot keep an eye on the energy that is being exchanged. So, but instead, what is more convenient is to fix the temperature, right? Let the energy vary, but you can fix the temperature. How you can fix the temperature? So you attach your system to a reservoir, to a heat reservoir, okay? So that the temperature will be maintained, but the energy can vary from, energy can vary from 0 to basically infinity anywhere, okay? And so if you have this kind of system, then it is called canonical ensemble. It is characterized by canonical ensemble, okay? So ensemble, you guys understood what ensemble is, right? It is just mental copies of the same system, okay, over which the system, over all the states, that all the micro states that system can access. Those are called, those constitute the ensemble. Let me know if you want to, if you didn't understand what ensemble is, because it will be very important to solve the problems, okay? Okay, so yeah, so ensemble is basically what? Mental copies. So you make copies of the given system, and all of these copies will have different microstates, okay, with different microstate. Microstate is denoted by omega, okay? Because we know that on an average, what you measure is an quantity averaged over time, so in which your system passes through, okay? And all those all those configuration of your system constitute particular microstates. So instead waiting for infinite amount of time, we make infinite copies of the system, each with a different microstate, and we call it ensemble. And then we measure everything. We take average over those ensemble, whatever physical quantity that we want to measure, like entropy, energy, or anything that you free energy, Helmholtz free energy you can calculate, Gibbs free energy you can calculate, taking average over all those ensembles, okay? So okay, so microcanonical ensemble we recapped last time. Okay, so today let's discuss some things about the canonical ensemble. Okay, so like I said, the canonical ensemble is where the energy is variable but temperature is fixed. Okay, and now you can ask a question that, okay, so what is the probability that at any time t a system, because now the energy is changing, right? We have not fixed the energy can change over any value. So the question is, what is the probability that at any time t a system in canonical ensemble has energy, suppose er, okay, and let's denote this probability by pr. Okay, so this is the fundamental question about canonical ensemble, that you have many systems. Okay, you have a canonical ensemble and each of them will be in some energy, with some different energies, right? Now we want to, like this, there will be some er. Now we want to ask that what is the probability that if at any time t you go and measure the energy of the system, you will find that it has an energy er, some energy er, and that probability we are denoting by pr. Okay, and so I mean you can derive this. I'll just this has been done in the lecture, so I'll just write. So this is directly proportional to, this probability is directly proportional to exponential, okay, and of some constant beta. We will see what this beta is, and the energy of the system. Okay, so this is the answer. Now you can remove the proportionality constant by so you can basically normalize it, because you know the probability, the total probability should be 1, so that will become so this will be your normalization constant, sum over all the states. Okay, so that if you sum it over, you will get 1. Right? So this is the probability that a system in canonical ensemble has energy er. Okay, is this fine? And this summation is over all the states accessible to the system, which you can say is, it is the sum over all the ensemble in the all the canonical ensemble, each particular system collection of canonical ensemble. Okay, so yeah, this is a very important result. You should remember it. And then if someone I mean, if you then you can ask, what is the, what is the expectation value of energy? Like, if you measure, what is the average energy simply? We denote average by this angle brackets. Okay, so what is the average energy that you will, I mean, if you wait for a infinite amount of time, or you sum over the energies of all the system in the ensemble and divided by the number of system in the ensemble, what will be the total energy? What will be the, average energy basically? And this is what we denote by, total, by the energy, internal energy of the system, right? And so this will be, so I'm writing it, let me know if you understand this. Okay, so this will be sum over all the states, energy of particular states, and probability of that state. This should be the average energy. Is this fine?
Sir, does this expression represents the average energy of the whole system?
Yes,
Okay, sir. Thank you.
because I mean, so one way to, understand this is, so let's expand it. So you will get E1, P1, then E2, P2, and like this, right? And like, suppose there are n ensembles, so the last one will be En, Pn, right? Like this. And all these probabilities will be, like, there will be higher probability to get E1, E2, but all of, I mean, the sum of all the probabilities P1, P2, up to Pn should be 1, right? And so this is like, this is like a partition of your energy. Okay, you have done a partition of your total energy into n number of systems. And so this can be written as, because we have found the expression for PR, so you can write this like this. Okay, and further you can write it like this also. Is this fine? How you go from here to here? If you differentiate this quantity log of, then you will get this one. Okay, so just make sure that you are able to understand it, otherwise I will show you. So till now we don't know what beta is. Okay, it's just some constant. We will see, I mean, what beta is. So let's call it equation 1. Now you know that the Helmholtz free energy is given by this expression, right? And if you take differential change, this will be I mean, let me do it. So du minus tds minus std, right? And then from first law of thermodynamics you can replace the du by tds minus pdv plus mu dn, okay, and then you have minus tds minus spd, so this goes out, so you are left with std minus pdv plus mu dn. Is it okay? Now so from here you can write entropy. So these things have been done before, but just I'm writing it again. And then pressure can be written in terms of differentiation of Helmholtz free energy and the chemical potential also, right? And then you can invert this formula to get internal energy. So this we will need later on when we will solve the problems, you will see. But yeah, let's write the expression for internal energy. So from here we have just inverted it, okay, to find the internal energy. And so this is this, and for entropy let's put this value, okay. And now this whole thing can be written as like this. Is it fine? If you differentiate it, you will get back this thing, okay. Just try it. And so further you can write internal energy as, and this thing again can be written as this, okay. You can check this also. And so if you now you compare, so this is equation 2. If you compare equation 1, which is here, this is also expression for internal energy, this is also an expression for internal energy. If you compare both, let me see if I can them in. Yeah, if you compare both, you can see that log of this thing is equal to f by t here, right? And beta is looking like 1 by t here, right? So what we can do is we can multiply both numerator and denominator by a constant k, okay, and we can write, so comparing 1 and 2, beta is 1 by kt and f by kt is equal to log of this thing, right? Log of sum over all the states, okay. So now you see you have an expression of Helmholtz free energy. Sorry, there will be a minus sign because, yeah, here is a minus sign, so this is a minus, there is a minus sign, kt ln qn vt, where this qn is this quantity, okay, and this is what we called up partition function. Okay, and once you find this partition function for any system, you can find out, Helmholtz free energy, and from Helmholtz free energy you can find out entropy, pressure, chemical potential, anything that you want to calculate. I mean, all the thermodynamic quantities. Also, you can find out, specific heat, because specific heat is given by del U by del T, and U is given by this quantity here, so this becomes this, right? So in principle you can find all of these things. So these are, response function also you can calculate just from a partition function. So now you see the relation between statistics and thermodynamics here. So this is purely a statistical quantity, this partition function, right? You have constructed an ensemble, and then you ask that what is the probability that a particular system in the ensemble has energy ER, and you found this answer, and the sum of these quantities is called partition function. Okay, and once you find this partition function for any system, you in principle know everything about the system. Okay, all the thermodynamic quantities you can calculate. So these are very important results. Is it fine?
Yes, sir.
Okay. Now one more thing you can see from here, very important result, is that, so since this probability PR, now we can write it like this. So because partition function we are denoting by Qn, so Qn minus 1, and this, right? We can ask what is the expectation value of log of this PR, log of this probability. That means yeah. So yeah, so log of PR, how do you write it? So similarly, I mean, like we calculated the expectation value of energy, you can write it like this, right? So this is PR log of PR, right? Is this fine? And from this expression, what you get, so if you take log of PR, you will have minus log of Qn minus beta ER, right? And if you take average on both sides, so this quantity is fixed, right? I mean, this is sum over all the states, so this will not have, I mean, this is a constant, only this will vary, right? Energy is varying, so you have to take average over energy. And so we can basically equate this and this. But wait, what further we can write? So log of Qn is from here from here, log of Qn is what? F by Kt, right? And this is just the internal energy, right? And so you can equate this and this, and what you get is, oh wait, and also you can do, what you can do is, so 1 by kt is just beta, right? So beta f minus beta u, beta you can take outside, f minus u, and then this you can write minus s by k, using this. Is it fine? So that means now if you see from here, entropy is simply k right. We have equated this and this. Now this is a very important result. You see, entropy is a thermodynamic quantity, a state function, and now it only depends on a probabilistic quantity. I mean, on a probability, right? So this is very interesting. So entropy solely depend on PR. What is PR? PR is the probability of the system being in different states accessible. Now from here you can ask, then what does entropy mean? So what is the physical meaning of entropy? From here you can understand, right? So suppose, so now think of a system which can take only one energy, which has only one configuration, that is PR is just 1. Such a system can be an ideal gas cooled down to 0 temperature, so that it doesn't all the molecules of that gas has to acquire the 0 energy state. So it has only one choice, and so probability is 1, right? And so entropy will be 0. And as you raise the temperature of that system, now the molecules can go to higher energy states, and it have many choices of energy configuration. So now the entropy starts increasing, and so randomness comes into the picture, disorder comes into the picture. Okay, so the more choices of the more choices you have in a system to attain a different configuration, the more entropy is there. Okay, so this is how you can interpret entropy based on statistical mechanical formula. And now you might say, sir, last time we for the macrocanonical ensemble, the entropy was given by this formula, right? This was for macrocanonical ensemble. So how does this relate to this? So actually this one is, this is in a special case of this formula, as you can see very simply. So we know that for microcanonical ensemble, I don't know if you remember, but we studied that the microcanonical ensemble, all the configuration points, they flow like an incompressible fluid, right? Do you remember it? In the phase space, they flow like an incompressible fluid. That is, all microstates of each member of the ensemble are equally likely to occur. Okay, so probability is given by just the 1 over number of microstates. And if you put that in this equation here, you will get this same answer. So this is a general, I mean, this is a general scenario, okay? And microcanonical ensemble is just a special case where all the microstates for each member of the ensemble are equally likely to occur. Each member of ensemble are equally likely to occur. Okay. Okay, and then there are some special cases, like if you have a non-interacting indistinguishable set, I mean, collection of particles, then the partition function will be, I mean, the partition function of n such particles will be equal to partition function of one such particle to the power n by n factorial. And if these are distinguishable, that means you can tell one apart from other, then for n such system, the partition function is just the n times the partition function of one such system. Okay, so this is also we will use these results. So I'm not deriving these quantities. These are done in the lectures, and you can find them in any standard book. I'll just use them while solving problems. So shall we go to the problems now, or do you have anything to ask?
Sir, Q1 can be the partition function of the first HML or any of the.
Anyone, because see, if you have indistinguishable particles, I mean, they should all be identical. Okay, they should all be identical particles. So any one particle you can choose of so suppose you have an ideal gas. Okay, you can choose a single particle that so Q1 will be the partition function of that one particle. Okay, so this will be more clearer when we solve the problem. Okay, so let's go to the problem. Okay, so yeah, so the first problem, we have a magnetic system, one dimensional magnetic system of n localized spins. Okay, so you have a n localized spins, an array of magnetic spins. Okay, and temperature is T. So see, temperature is fixed. So once the temperature is given, you will, I mean, immediately know that this is a canonical ensemble, and Hamiltonian is given here, so you can calculate the energy based on the Hamiltonian. Okay, so Hamiltonian here is given, and these are parameters which are constants, and sigma I, which are there, can have plus or minus value. Okay, for all the different spins, I mean different sides. Now assuming that n is even, so there are even number of spins, and you note there that this sum is over odd spins, odd number of spins. Okay, we have to find the expression for partition function for this system. So how to do this? So first of all, let's write the expression for partition function. This is just this quantity, right? Now Hamiltonian is just you know is a proxy for energy, right? So and here our system is made up of spins, so sum over all the spin states, and so this box is this is the box here, so I'll write it. This H is different from this H. This is the Hamiltonian H, okay? Now you see these are localized spins. That means they are fixed in space like this. So you can distinguish them, right? So for you, Qn should be Q1 to the power n, right? And here we will have to, now this Hamiltonian, it depends on, see, pair of spins, qi plus 1, okay? So you'll have to be smart, and you will have to choose your single system or your single spin system as a pair of spins, okay? So that means let's consider a pair of spin any general pair, sigma I and the one after that, sigma I plus 1, okay? And if you just write the Hamiltonian for this pair, okay, so the sum will go away, so minus j sigma I plus 1. We are writing the Hamiltonian for just one pair, okay? We are not summing over all the pairs. And this we have to sum over the two system that we are taking here, two pairs that we are taking here. Is it fine? For a single pair, this is the Hamiltonian, right? Is it fine? I have removed
Yes, sir.
I have removed the summation, okay? Now we have to find the possible states for these pairs. So what will be the possible states? So let's write sigma I plus 1. So they can be either both 1 1 plus 1 plus 1, right? In that case, what will be the Hamiltonian? This will be minus j minus, so this will be 2, so minus 2 mu naught h, right? Or they can be both, or they can be 1 plus 1 minus. In this case, Hamiltonian will be, so this will be 0 then, right? And only j will remain here. Again, this could be minus 1 and the other one be plus 1. In this case, again the Hamiltonian will be j only. And if both are minus 1, then in this case Hamiltonian will be minus j, and this is plus 2 mu naught h, right? So these are 4 possible configuration. That is 4 possible ensemble that we have. So the partition function for the pair, for one pair, this is just should be the sum over all the pair, Hamiltonian of the pair, right? Is it fine? Sum over all the pairs, possible pairs that are there, which will be, so so there are 4 pairs, so there will be 4 sums. So I'll just write them. So twice, because we have two states with the same Hamiltonian, and then we have beta j minus 2 beta mu naught h. Okay, and if you calculate it explicitly, you will get so this plus this, you can combine them and write as cos beta mu naught h, 2 beta mu. E plus exponentials you can write in terms of cos h, right? Cos h. Is this fine? And so your total partition function will be q pair times, so number of pairs, how many number of pairs are there? So since there are n spins, there will be n by 2 pairs, right? So your total partition function will be pair times pair to the power n by 2. Oh, so yeah, that is fine. And so you just this is your total partition function, which is this option. Let me know if you didn't understand any step. Is it fine? Nice. Okay, so let's go to the next problem then. Okay, so now we have the partition function. I told you, if you have a partition function for any system, you can calculate all of the thermodynamic quantities. So now the question is, what is the entropy per spin? Okay, so we know the formula for entropy, right? We, in terms of, this formula we can use, because we can write Helmholtz free energy in terms of partition function from here, right? And we can calculate entropy. So let's do that. So first let's write the Helmholtz free energy. So Helmholtz free energy is simply, but wait, it is asking at temperature T and H is equal to 0, right? So let's first find the partition function at H equal to 0. So at H equal to 0, partition function is very simple. It is just 2 to the power minus beta j plus, this one is 1, right? H is, if you put H0, this will be 1 to the power n by 2, and again you can combine them together at cos h beta j whole to the power n by 2. Okay, and now you can calculate the Helmholtz free energy, which is just kT ln Qn, and So if you take log of this, you will get kT n by 2 log of 4 cos h beta j, right? And then you can find I mean, you can directly differentiate it with respect to temperature. Yeah, with respect to temperature to find the entropy. Or what you can do is you can first find out internal energy, which is given by del beta of ln qn, right? So if you differentiate ln qn, what you will get? So why we are doing this? Because entropy is del f by del t, and here we have beta. So and beta is what? Beta is 1 by kt. So differentiating this with respect to temperature will be little complicated, but differentiating this with respect to beta is very easy, right? And so that's why we are doing this. And then we can use this formula, f is equal to u minus ts, to calculate our entropy. So you will see how we do that. So yeah, so differentiating this will give you, so simply del by del beta, so log of 4 cos h beta j. So cos h, differentiating cos h gives you sin h, right? So and since it is log, so cos h will first come down, okay, and yeah, and here j will come outside. You will get sin h beta j, right? Yeah, so this will be minus n by 2 j tan beta j, tan h beta j, sorry. Is it fine? Let me know if I did some mistake. And then from here, entropy is what? Entropy is u minus f by s, right? Sorry, t, u minus f by t. So s is one by t. So u we have calculated here, minus n by 2 j tan h beta j, and f we have calculated here, which is n n by 2 kt ln 4 cos h beta j, right? And entropy per spin, which is small s, is just s by n. So you just divide this by s by n, and you will have your answer. Okay. Is it fine? So we did not use this formula. Instead, we calculated internal energy because it was easier to differentiate with respect to beta as with respect to temperature, this quantity. And then we used this formula. fine? Okay, thank you. So now let's go to the next question. So this is also based on the same problem. Okay. Yeah. So here the question is what will be the magnetization per spin? Where magnetization is defined by, I mean the definition is given here. It is just this quantity. So this is the average over sum of all the spins 1 to n. So we have to find the magnetization per spin. Okay. So this is, I mean, this looks trivial, but let's see how to deal with this. So no. So this quantity so as we written earlier, this has, you know, exponential we calculate, you know, average of any quantity like this. So we can write similarly for this also, right? And so this is just 1 over qn sum over this quantity mu naught sigma I e to the power minus beta h, right? Sum over all the spin states. And we know this, we have already calculated this partition function, so which is this quantity, right? So first let's let's calculate this quantity for a pair of spins. That means like we did for while we were computing the partition function. So let's first calculate this. So this will be similarly, so mu naught is constant, so it will be outside, and q of a pair, and then so this is the q, this is the partition function of the pair that we have calculated earlier, right? And you can check that this will be just this thing, okay? And the total magnetization will be what? Will be just sum over all the pairs, right? And since all are identical, it will be just n by 2 times this quantity. So n by 2 times so q pair is this, and on the numerator you have 2 mu naught sine h, this is h, 2 beta mu naught h, right? And you can simplify this little bit, so 2 cancel out, this cancel out, so you are left with n mu naught sin h 2 beta mu naught h, here cos h 2 beta mu naught h plus 2 beta j. Yeah, so this is the total magnetization. This is the and then you can divide this by n, because you want to we want to know the magnetization per spin, so this n will go away and this will be the total magnetization per spin. So I think the correct answer is this one. Is it fine? So what we did is just we calculated this quantity for a pair of spin, okay, and then for all the, since we have n by 2 pairs, we multiply this quantity by n by 2 pairs, and we divided by n for to calculate to calculate the magnetization per spin. Okay, this is just the simple calculations you have to do. Is it fine? Okay, let's is it fine? You have any question? See, this was very difficult to calculate, right? But we know that, we can, but we know that partition function for the whole system is given by partition function of one system to the power n by 2, and that we use this information, and our one system here is the pair of spins. So we calculated this quantity for a pair of spin, and then we just multiply it by n by 2, since all the pairs are identical, so the magnetization will be just n by 2 times. Okay, please ask if you have any question. Okay, if you have not, then let's go to the next problem. Yeah, so here this is a application based question. So statistical mechanics can be applied anywhere, so this is just an example how we can apply it in biology. Okay, so suppose, so there is a process of DNA unwinding. So DNAs are folded like this. Have you seen the picture of DNA? They look like a zipper, and they can unfold. I'm not able to draw. So it will be like unzipping of a zipper. So when you put on a jacket, you zip your jacket, right? And so when you unzip it, so the links get broken between the two side of your zips. So suppose there are n links, so these are links, right? And either they can be so there will be two states of these links. So closed state with, so this is closed state and this is open state. Here I have shown the open state. Okay, so these are open state. So closed state with energy 0, open state with energy E. Okay, and it is required that the zipper only unzips from one side. Okay, so only one side, say from the left, and that the link can only open if all links to the left of it are already open. So a particular link will open only if all the links that are left to it, means that are above to it, are open. Okay, so we have to find the partition function of this system. Do you understand the problem? It looks very complicated, but the answer is very simple. Okay, so the zipper has n links. Okay, and zipper opens from the left, and if n links are open, then remaining n minus n links are closed, right? And energy, what is the energy of open and closed links? So if n is open, n links are open, then energy is, total energy is what? N times epsilon, right? And so our partition function, only consists of those states which are open, those links which are open, because the closed links have zero energy. So this will be just, this will contribute to nothing, right? And you can write it beta e to the power n. So this is constant, this is to the power n, so this is like, x to the power n. So it is a geometric series, and the geometric series sum is given by this, right? So here the x is this quantity, so q is simply 1 minus e to the power this is your answer, which is option 2. No, sorry, option 1. Okay, this is fine, but do you understand the problem? What is one system here? I mean, how do you define here a system? This is a chain of DNA, okay, and the question says that you are unzipping it. So suppose, so here one system is, one configuration of the DNA. So suppose, so let me denote some system. So let me try my best to draw it. So this is a system with energy, and this is going on and on. Okay, sorry, yeah. This is going on and on up to n links. So these are, n links that you have, and this has energy 0, right? Because all are closed. Now you are unzipping it. So suppose you first unzipped the first links here. Okay, so this is now open, but all others are closed. This one is open, but all others are closed. This one has energy E. Now you can open 2 of them. So 2 of them are now open, but now others are closed. This will have energy 2E. So all of these are your, systems in the ensemble. Do you get my point? Yeah. And so in general, the energy is n times E, okay, when n links are open. So that's why our partition function is given by sum over this thing, right, where n goes from 0 to n. So all these are summed over. Did you get my point? And then again you can calculate all the other things. You can calculate entropy for this system, you can calculate Helmholtz free energy, and so on, right? So yeah, I'm not going to do that. I just wanted to give you some idea of what partition function means and how to find it for different systems. And then there are very trivial systems which are very easy to calculate, like ideal gases and simple harmonic oscillator. You can find those problems in any standard book. uh, so yeah, please, if you have any question, please ask. Hello. Okay, if you don't have any question, then I'll close the session today here, and we'll meet again tomorrow. Sorry, next week. Okay, so bye. See you. Thanks for joining.